Okay, and here you are, and here I am. Another video on chapter 4. We are on section 2. This is the second video of this section. And where are we? Well, if you recall, last time I spoke, last time you listened, we were discussing the idea of a null space. Right? And if you have to, I'm going to give you just a real quick review. But if it's been a little bit since you've watched that video on null space, you may have to go back and brush up or look at your notes, because we have one more problem, one more example dealing with null space, and then we're going to introduce a brand new space and contrast them. Okay? So really quickly, remember the null space. Right, I'm going to go ahead and highlight here. The null space of some matrix is a subspace of Rn. Okay. In other words, or equally said, it's the set of all solutions to a system where you have a matrix A multiplied by a vector x equals 0. Now, I tried to build an analogy where last video, and the analogy basically said that if we think about it using Netflix, if we think about when you first log into Netflix, the suggestions for you, for video suggestions that you might like, we could think about that as the 0 vector, right? And that's the initial suggestions before you have any viewing history. So the idea of the null space could kind of be thought of as, since you have ax equals 0, you could kind of think of it as the solutions, or the what set of movies would you have to watch in order to reset all the suggestions that they have for you all the way back to 0 when you first logged in, right? So now, whether that it's doable or not, that I don't know, but it's at least gives you an idea that you're dealing with the solutions to the equation ax equals 0 when you're dealing with the null space. So no more of that. Let's continue with one more example of null space. So the question asks us to find a spanning set for the null space of the following matrix, right? So the first thing I want to make sure you know is, what do they mean by a spanning set, right? Because we can't really proceed if we don't know what they mean by a spanning set. So we've talked about this many times, but a spanning set is going to be the linear combinations. And if you still, again, it's always helpful if you took my advice and you had some type of vocabulary journal where you could grab these vocabulary words when you need them. Otherwise, man, it's like it starts to get very hard to cipher through the lecture material. And it's not that you don't have the capacity to learn it. It's these it's this jargon, it's these words that I keep using, and without a command of that vocabulary, it starts to get extremely confusing, and you can't pick up on the new material. So what do they mean by a spanning set for the null space of matrix A? A spanning set, okay, is basically the linear combinations, right? The linear combinations that would span all of the null space. So in other words, there is some set of vectors, we don't know what they are yet, but there's some set of vectors out there that you could use those vectors along with a scalar, and you could span or reach every point that is in the null space of this matrix A, okay? So how do we proceed? Well, the good thing is, if you want to be able to find the linear combinations of a matrix, we can start by using that algorithm, matrix algorithm, to row reduce this matrix, right? And so what I'm going to do right now is just give you the RREF form, the row reduce echelon form of this matrix. And it would look something like this. So 1, 0, 0, negative 2, 0, 0, 0, 1, 0, negative 1, 2, 0, 3, negative 2, 0, and 0, 0, 0. And now how do we get there? Well, so basically, since we're dealing with ax is equal to 0, in this case we have a and we have 0. So you would be taking your coefficient matrix. In other words, listen to me. What I'm commenting on right now is how did I go from here to here? Well, I added one more column that would represent the solution column, right? So I turned the coefficient matrix to an augmented matrix and then row reduced. All right, so at this stage, so this is the row reduced echelon form of the matrix. And what I want to do right now is go ahead and rewrite this as a system, okay? Because in other words, you're looking at your calculator. Your calculator is giving you this screen, but sometimes we lose sight of the fact that we're actually still working with systems, right? Systems of linear equations. So notice what I'm doing right now. We have 1, 2, 3 rows. So that would mean we would have 3 equations. Except we don't need the last row, the third equation, because it's all zeros. So we really only have 2 equations. But now how many unknowns? So notice that the equations represent, or I should say the rows are going to represent how many equations that you have in your system. And the columns represent the number of unknowns, right? So each column there represents an unknown. And I'm going to draw a vertical bar so that you can understand that this is an augmented matrix, and so you can separate the solutions from the variables. So now I've already actually, let me make sure I don't do anything silly here, okay? Because when I talk and write, things can go bad. So I have x sub 1 minus, so x sub 1 minus 2 x sub 2 minus x sub 4 plus 3 x sub 5. So I have 5 columns, therefore I have 5 variables. All right, now let me go ahead and grab that second row. I'm going to turn that second row back to a system. So I have 0 x sub 1, 0 x sub 2, I have 1 x sub 3, I have 2 x sub 4s, and I have negative 2 x sub 5s. Okay. So, I mean, you can always write 0 equals 0 if you'd like to think of, if you like to set your system up this way. But now, at this stage, do you notice that we've gone back from, we've basically gone from a row reduced matrix back to a system, so you can see it more clearly as to what's going on here. So, okay, now what? Now what do we do? Well, don't lose sight of the goal. The goal is to find a set of vectors, right? I'm trying to find the set of vectors that would span this space, this null space. So I'm going to go from RREF matrix to system, and then I'm going to go from system to the general solution. So let me ask you a question. How many free variables do I have while I'm here? So I have, what is the number of basic variables? What is the number of free variables? So while I'm writing this out, maybe you can take a look above at that matrix and try to figure out how many free variables that we have. Okay, so the number of basic variables, and so if you have, think about it, if you have two equations, all right, forget about the zero, forget about the last row, forget about all zeros. If you have two rows or two equations, then you have two basic variables, okay? At most two. If you have, but we have 5, so that would mean that we have 3 free variables. Ready? So now let's get to our general solution. So when we set up our general solution, we're just going to solve for each variable, x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. I have 5 variables. I'm going to solve for each. Now, let's start with solving for x sub 1. So in this case, what you're going to see me do is, if you kind of, if you follow me up here to this equation, I'm going to solve this equation for x sub 1. I'm going to take every other variable in this equation and bring it to the right side. So now we have 2x sub 2 plus x sub 4 minus 3x sub 5. All right, now let's take a look at the second equation. So notice in the second equation there is no x sub 2 variable, right? There's no x sub 1, there's no x sub 2. So I'm going to solve this second equation for x sub 3. So in this case, x sub 3 is going to be equal to negative 2x sub 4 plus 2x sub 5. Okay, now every other variable in this system is what we call a free variable. So as I've undoubtedly said many times before, notice how your basic variables are always defined in terms of your free variables. So if you and I play a game and I ask you what is x sub 1, the first thing you should tell me is, well, I can't tell you what x sub 1 is until you give me an x sub 2, an x sub 4, and an x sub 5, right? All right. So what we want, we're still trying to be able to get to the set of vectors. So to go from general solution to the spanning set, let's imagine that sometimes this is helpful if you think of it like this. So I'm gonna start here. This is an optional step. And what I'm going to do is, what I'm about to write in this matrix here is the right-hand side of each of this general solution, right? So we still have x sub 1 equals, but let me now go ahead and write it as x sub 1 equals what? It equals 2 x sub 2 plus x sub 4 minus 3x sub 5. Now, this next step, it can be confusing to some students. So what would I write in this entry right here? Well, I don't write free if I'm trying to put it back into a matrix, right? I mean, when you have the general solution, it's perfectly fine to make a statement about x sub 2 being a free variable, but you can't write the word free inside of a matrix. The matrix is not going to understand what you're talking about. So if x sub 1 equals 2x sub 2 plus x sub 4 minus 3x sub 5, what does x sub 2 equal? Well, x sub 2 equals x sub 2, right? Does that make sense? Let's continue. X sub 3 is equal to negative 2 x sub 4 plus 2x sub 5. And then x sub 4, obviously, it's just a tautology. It's an identity. X sub 4 equals x sub 4, and x sub 5 is equal to x sub 5. At this stage, right, this was an optional step, but I think you'll find it's just easier to go from where we left off to this where we want to be. So what I'm going to do is, you could think of it like we're setting up a linear combination. Okay, and we're setting up a linear combination. And remember that a linear combination is just a scalar multiplied by a vector, right? Or we should say the sum of scalars multiplied by vectors. But notice that I'm using the free variables as my scalars. So the question now becomes, well, what is going to go in each of these vectors now that I have my free variables acting as the weights or the scalars? Well, let's think about the x sub 2. So I'm going to go down, what I'll do is I'll go down, I'm going to be going down the line here, down each column, and let's figure out how many entries should go into the x sub 2. So let's start with the row 1. Is there an x sub 2 in row 1? Well, yes, there is. In row 2, is there an x sub 2? Yes, there is. In row 3, is there an x sub 2? No. In row 4, no, x sub 2. In row 5, no, x sub 2. So when I set up this vector here, we should start off with 2, because there's 2 x sub 2's in the first row. Then 1, there's 1 x sub 2 in the second row. And then 0, 0, 0. There's no more x sub 2's. Now let's go to the next free variable, x. So x sub 4, so we're going down the line. There's the first row has 1 x sub 4. The second row has 0 x sub 4's. The third row has negative 2 x sub 4's. The fourth row has 1 x sub 4. And the fifth row has none. And finally, let's go down the line with x sub 5. So I have negative 3 x sub 5's in the first row, 0 in the second, 2 in the third row. I have 0 x sub 5's in the fourth row, and I have 1 x sub 5 in the fifth row. Now, you are actually done at this point. You have done all the heavy lifting. But let's go back to the question was to find the spanning set. So I need to actually be able to write a set of vectors that spans the null space of that matrix. So to make this easier, I'm just going to call this vector U. I'm going to call this vector V. And I'm going to call this vector W. So, are you ready? What is the set of vectors that span that matrix? Well, I would need U V and W. Does it make sense to you that with these three vectors, all right, so and having scalars, any scalar that I want, with those three, the linear combinations of those three vectors, I can reach every single point in the null space of that matrix. I hope that makes sense. It's if not, you could always rewind it and go a little bit slower. But now what we want to do is we're going to introduce a new space, right? A new type of space. And I'll give it a name in just a second. Before I do any of that, I will go ahead and I'm going to introduce the new space, which is called a column space. I'm going to already assume that between vector spaces, subspaces, null spaces, and now a column space, you're starting to get confused. So I'm going to take a second and make sure you understand some of this vocabulary before I continue, okay? So we have a new type of space, the column space. And I'm going to read this to you, but please understand, I already know that, I would be highly impressed if at first read this is not starting to confuse you. Okay, so let me read, and then we're going to slow down and try to make sure we understand what's going on. So the column space of some m by n matrix A. Okay, so this is the way that we write or we denote the column space. Is the set of all linear combinations. So there's linear combinations of what? Well, this time it's the linear combinations of the columns. Now, let me go ahead and assume that there's confusion, and let's see if I can do my best here. Are we ready? So just pay attention really quickly. Look, here's some matrix A. Now, I don't know what it looks like, but I know that there's m rows and there's n columns. Now, hold on for a second. You keep hearing me talk about Rm, R space Rn, or Rm. Let's get a grasp of that right now, okay? Every time I talk about this, it spans Rm or a subspace of Rn. I don't want any more confusion. Are you ready? So, do you agree with me that R2 is two-dimensional space, right? R3 is three-dimensional space. But what is Rm? What is Rn? Well, it's simple. It's just the space right? It's just whatever space. Could be two-dimensional space, three-dimensional space, four-dimensional space. It's just the space that is determined by, determined by what? By m rows. So it's the space that is determined by the rows of matrix A. Right? So if we have 3 rows, then Rm is R3, three-dimensional space. If there's 2 rows, then Rm is two-dimensional space. Obviously, Rn is the space determined by the columns. So by the columns of A. Okay, so now let's go backwards really quickly, and we're gonna build a little bit more. So the column space, what I've highlighted here, is the set of all linear combinations. Now, when you hear linear combination, every time you hear linear combination, you should be thinking, oh, that's just C times, I'll write vector, I'll use v and u just like I did before. When every time you hear linear combinations, you should be thinking that's just scalar times vector plus scalar times another vector, right? It's the set of points that you can reach through two operations, vector addition and scalar multiplication. Now, when it says the column space, this is a set of all linear combinations of the columns of A. So when you start thinking about the columns of A, that's n columns. So let me make up something here. Are you ready? So let's pretend A is a 2 by 3 matrix. I'm going to erase this in just a second. How many vectors would you assume is going to be in the column space of A? How many vectors would you assume would be in the null space of A? All right, now we're going to come back to that question, but you feel free to take a guess based on what I've been trying to teach you right now. How many vectors, right? What is the how many vectors would you assume would be in each of those spaces? All right. So I want to go ahead and make a statement that the span of any set of vectors is a subspace. Now this is something we've alluded to many times, many times. But it meets all, remember, it meets all the criteria that you need. So the span of any set. So here's a any set of vectors is a subspace. So the span, since the span is just the linear combinations, can I get to 0? Of course, right? Just pick 0 scalars, and so forth. Closed under multiplication, closed under addition. Okay. So now let me read a theorem that kind of is born out of this. So every set of vectors is a subspace. Well, what's a column space? What's a set of vectors, right? For sure. So then obviously the column space is going to also be a subspace. A subspace of what? A subspace of Rm. Now, maybe you're sitting here thinking, wait a minute, that doesn't make any sense. If you're thinking there's n columns, but there's an m rows, why would the column space be dealing with Rm and not Rn? Maybe that's your question. Well, wait a minute. Can you pretend for just a second that you reach your hand in here and you grab one column? Here's the column that you just grabbed, okay? Now, how many entries are in this column? Well, let's just say there's an x1, x2, maybe an x3. So what space would this be? This would be R3. But do you see how the m, the number of rows of each column, will end up determining the space that the column is in? Right? Let's imagine the column would look like this instead. Let's imagine it looked like this. So you reached into the A and you grabbed a column. Here's your column. What space are you in? You would be in R2. That would mean there's 2 rows. So that's, I hope that makes sense, because that can be confusing because you think columns, there's n columns. Why are we in Rm? But that is the reason. So, okay. So one more time, the column space is the set of all linear combinations of A. So, linear combinations. So ready, let's go ahead and stop with the theory and jump into an example. Ready? So here is our first example of a column space. What are we asked? We're asked the following question. We're asked to find some matrix A. Right? We don't know what it is. Some matrix A. Find some matrix A such that, right? So such that W is equal to the column space. Okay. Well, what is W? Well, here they went through and they defined W for us. So let me write that and let me make sure we can understand that. So W is equal to the set of vectors. Now, and each vector would have 6a minus b for its first row, and a plus b for its second row, and negative 7a for its third row. And they tell us that, you know, set of vectors such that now the a's and the b's are real numbers. Okay. So I've rewritten this. I'm gonna erase what I just wrote because we already have it written. But that is how they're defining W. But what do you want? You have W. You're trying to figure out what matrix A is out there that has the column space W. Okay, so let me go ahead and erase this. And how do we begin this process? Well, let's go ahead and think of W slightly different. So I know I just wrote W, but now I'm going to write it just slightly different. So let's think about the restrictions on A. Well, no, I shouldn't say the restrictions on A, but let me think of it as the vector that you would multiply by A, plus we're trying to figure out the vector that you would multiply by B. Because I still want these conditions up here to be held, right? 6A minus B, A plus B, negative 7A. And of course I know that A and B are real numbers. All right, so let's start with the first vector. First row, what would you have to do if you gave me an A? What's the first thing I would have to do? Very first row, what would I have to do with some A that you give me? Well, I'd have to multiply it by 6, right? Now, second row, if you give me an A, what would I have to multiply by A? Well, it's just 1, right? Third row, if you give me an A, what would I have to do to that A? I'd have to multiply it by negative 7. All right, well, what about B? So, again, I'm looking at this. I'm looking up here. What's the very first thing, if you give me a B, that I would have to do to that B? Well, I'd have to multiply it by, since it's minus B, that means I'm multiplying by negative 1. And second row, it's plus B. So I don't have to do anything to that except in the second row. Now, in the third row, notice there is no variable B. So if you give me a B and I'm working with the third row, we can just think of it as I would have, since there is no B, I would just zero that out. All right, well, we're getting somewhere. So look, now we have A multiplied by 6, 1, negative 7, plus B times negative 1, 1, 0. And guess what? Those are the vectors, right? Those are the vectors that make up A. So remember, A equals something, so some M by N matrix, and guess what? That's your, you can say these are your columns of A. So in the beginning of this problem, if you asked me what is matrix A, I had no idea. But now I do. I know matrix A has 2 columns. And I even know what the columns are. So there's my matrix A. All right, that is, so I'll write one more thing so that we are done with this problem. Just understand that a linear combination is the same thing as the span, right? So what I wrote here can be written as span. That's not, by the way, that's not span, that's san. I can be rewritten as span of those 2 columns, those 2 vectors. Okay. So let's go ahead and go to where I want to go. Actually, no, let's go ahead and take a break. And when I come back, I'll do one more video. And the last thing that I really want to do is contrast a null space and a column space just to make sure you get it. Okay? See you soon.